Hello and welcome to our discussion on dividing polynomials and rational zeros test. Basically, we're just going to look at a bunch of different ways to find zeros of polynomials and be able to find factors of polynomials, which is a very important thing to be able to do, not only in algebra, but on through to calculus and physics and chemistry and biology and a lot of other subjects. Okay, so first of all, let's get some of the definitions out of the way. What does it mean to be a polynomial factor? Well, we get this great math gobbledygook that we always get where they try and confuse us with a bunch of symbols and stuff, and they tell us that some polynomial d of x, right, that's just the name that they're going to give our polynomial, is a factor of some other polynomial, call that f. If there's a third polynomial, okay, great, so now they got three of them, right, such that this happens. Well, this is really kind of a no-duh definition because think of it this way. We know that 3, right, is a factor of 12 because 12 equals 3 times 4 and there's no remainder, right? No remainder. That's what it means to be a factor, that you basically can divide the number by the other number and you get a result without a remainder, right? You get a whole number. Well, when we're dealing with polynomials, it's kind of the same thing. We can take this f, right, which is the same thing as our 12. We can divide it by some other polynomial, d, which is the same thing as our 3. And the result is this third polynomial, which is the same thing as 4. And there's no remainder, right? So you can see that 12 equals 3 times 4. We're just doing it with polynomials now. Something as simple as we know x plus 1 is a factor of, let's say, x squared plus 4x plus 3, right? So here's my d, here's my f, and we know that that works only if there's this q, this quotient polynomial that works. So can we write x squared plus 4x plus 3 equals x plus 1 times something? And yeah, if you factor this out, here's my q. Okay? So that's all they're trying to say. Don't let the symbols confuse you. Okay, the division algorithm is just kind of restating the same idea of the factor, but in a more general sense. We're now going to allow for remainders. So we've got our polynomial, our f of x, right? Last time, that was the thing that was in green. We have this polynomial d, that was our yellow piece. And then we always say that the polynomial can't equal 0 because you can't divide by 0. And we're saying that if we take any polynomial and we divide it by any other polynomial that's not equal to 0, there's always going to be these unique polynomials left over, q and r. So they're basically saying take any polynomial, divide it by any other polynomial you want, and the answer is going to be another polynomial plus a remainder. That's it, right? So you can basically now list any polynomial as just a combination of two. So here's our product. Here's the d times q that we had from the previous slide. And then we just add in this remainder. And sometimes the remainder is 0, as we saw before, right? We had x squared plus, what was it, 4x plus 3 was equal to x plus 1 times x plus 3 plus 0, right? No remainder. Okay, and that's what they're saying down here, that either R is a zero polynomial, meaning that there's no remainder and meaning that, these two things are actual factors of f, or the degree of R has to be less than the degree of this d. So this is a degree of 1, so the only thing we could have been left with would have been a degree of 0, which means it had to be a constant. In this case, the constant was 0. But you can have other times where you can get a remainder. Okay, let's look at some examples. We can use long division and synthetic division to find the quotient and remainder when 2x to the fourth plus x cubed minus 16x squared plus 18, whew, that's a mouthful, right, is divided by x plus 2. So let's start by doing this one first with long division. Now, if it's been a while since you've done long division, it's long division of polynomials is the same thing as when you did long division with numbers. If we wanted to take, let's say, let's do 23 and divide it into some big number, right? 35709, let's say, right? The first thing you do is go, okay, well, 23 can't go into 3, so I gotta, kind of take the first 2 and go, okay, it can go into 35 one time, right? 1 times 23 is 23, and then you subtract, and you get 12. And you go, okay, well, 23 can't go into 12. Well, that's good, because if it could, I did this wrong, right? This piece always has to be smaller than that piece. So you have to bring down the next one, and now you do 23 into 127. And you go, all right, well, that goes in there 5 times. And then you do 5 times this. Well, 5 times this is 115. And then you repeat the process, right? This one minus this one, so you're left with 12. Bring down the 0. Oh, well, I know 115 works, so 5 works again. 115. Do the math again, right? Subtract it. 5, bring down the 9. Well, this can go in there twice. For 46, we're left with 13, and then here's my remainder, plus my 13. And we could write it as 35709 over 23, because that's what it means to be divided by 23, equals 1552 plus 13 over 23. Because this is how much, and then the remainder is always being divided by that thing. It's that leftover bit, right? Because the whole thing was being divisible by 23. So that's where this whole remainder over d comes from. It's that same kind of idea. Well, the same concept can be applied to polynomials. We want to take x plus 2 into 2x to the fourth plus x cubed minus 16x squared plus, and here's an important part, 0x plus 18, right? This 0x is a placeholder, just like this 0 was a placeholder, right? That means we didn't have any tens, right? We had 9 singles, no tens, 7 100s, right? 5 thousands, and then 3 10,000s. Well, this is a placeholder. It tells we have none of the x pieces, right? We've got this many x squareds, x cubes. So you always have to put in zeros for every power that's missing. So if you start here with 4, you got to have 3, 2, here's a 1, right? Power of 1. And then if there wasn't a constant, you would also want to put a plus 0 there. You have to have something for every space. And now the same rule applies. You have to take this and divide it into, you try into the first term. Can x go into 2x squared? You go, yeah, absolutely. It goes in 2x cubed times. Now, sometimes books and other people will put this number over x cubed. They'll kind of line up the powers. I just put it over the thing I'm dividing into. I know that over here, I moved it over 1. So to be consistent, I probably should move it over. Right? I got to break that bad habit that it goes here, 2x cubed. And then this times this, just like we did, right? 1 times 23. So this times this gives us 2x to the fourth, and then times this plus 2x cubed. Just like before, you subtract. Right over here, we subtracted it to get the next line. So you subtract it, those cancel away, and you get x cubed minus 2x cubed, right? Which gives you, wait, I did my math wrong, didn't I? 2 times 2 is 4, right? So you got to go slow and don't make mistakes like I do. Now when you subtract it, you get negative 3x cubed. Okay, and now the process repeats. This into this piece goes negative 3x squared times, bring down our next one, do the multiplication. Negative 3, right, times 2 gives us negative 6x squared. I like to change signs and add, right? If I'm subtracting, it's the same thing as adding a negative. And sometimes when you subtract a negative, you might forget that. So this is safer to keep you from making mistakes. So now I add, those go away. When I add these, I have negative, 10x squared. It's one of those days where I'm just going to be making mistakes all day long, right? Because negative 16 plus 6 is still negative 10. Bring down the 0. Repeat the process all over again. X into this goes negative 10x times. Again, that's a negative 10. You can change signs and add. That goes away. 20 plus 0 is 20x. Bring down your last 18 piece. Do the process all over again. Plus 20 gives you 20x plus 40, right? Change signs. This becomes a negative, right? And add if you want to do that, or just subtract it. But you basically have 18 minus 40, which gives you negative 22. And there's your remainder. All right, so we found the new polynomial and the remainder. And if we go to the next slide, we'll see the much cleaner version. But it's the same result, right? We got negative 22. All right, what about synthetic division? If you've never done synthetic division before, it's actually really awesome. It's really quick and easy. You're basically doing the exact same thing as long division. You're just not wasting time writing all of the x's, writing all of these letters. You're basically taking all of this and condensing it into something as small as this. Okay, so a couple things to realize. First of all, synthetic division only works when you're dividing a polynomial by x plus or minus some number, right? So x plus 2, x minus 7, x plus 3, x minus 5, whatever, but it has to be just a simple linear term here, right? It can't be x squared, it can't be 2x. There are ways to make it work with that, but it's really only effective and easy to do it this way. Okay, so that's the first rule. The second thing to pay attention to is the number you put here is always the opposite of this number, right? So basically, you're always using synthetic division with x minus c, okay? So over here, x plus 2 is really x minus a negative 2, right? So that means my c is negative 2. That's the first kind of stumbling block where students make mistakes. But really, if you just kind of pay attention to that one little minor blip and then learn the very basic algorithm, basic steps for how to do this, you'll see how brilliantly simple this is. Okay, so we know that we're dividing by negative 2. The numbers up here are just the coefficients. And again, just like before, you got to put in zeros for any missing things, right? So there's my 2, my 1, my negative 16, my 0, and my 18. That's where those come from. All right, so that part is pretty simple. Now, here's how it's done. You always take the first number and just bring it down. That's your starting point. Now it's very simply just multiply and add, multiply and add, multiply and add, multiply and add over and over again until you get to the end. Okay? So here's how it goes. Negative 2 times 2, negative 4. Add those together, gives you negative 3. Look at how that is this number right here, right? Okay. Multiply, negative 2 times negative 3 is positive 6. Add those together, negative 10. Hey, does that look familiar? Right. Once more, negative 2 times negative 10 is positive 20. Add those together. That looks familiar, right? And then last but not least, negative 2 times 20 is negative 40, right? Add these two together, negative 22, and lo and behold, the same number. See how much quicker and easier that is? So synthetic division is a beautiful thing. It's limited in its use. So anytime you're dividing a polynomial by what's called a monomial or a linear term, basically something that's just of the form x plus a constant or x minus a constant, you can use synthetic division, and it becomes a very time-saving tool. Okay, so we can see that in both cases, we got the same answer. Now, I didn't point this out on the previous slide, but here is a much prettier version of the synthetic division that we just did. And you'll notice that these numbers here correspond to these numbers here, and with your remainder. So not only does synthetic division give you the remainder, it also gives you the other piece, right? The quotient piece. Now, if we go back here, see, here's that same quotient. The 2x cubed minus 3x squared minus 10x plus 20. 2x cubed minus 3x squared minus 10x plus 20. Okay, so you get all the same things. So if we take our original polynomial divided by x plus 2, we get this quotient plus our remainder. Remember, our remainder is always divisible by that, or divided by that original thing. Okay? That's basically how to use long division and synthetic division to divide polynomials.